What happens? So when we're looking at melting point, we're concerned about the strongest force. The strongest force comes from the weakest bond. So we'd have to look at each of those structures and determine what bond was present in each molecule. Once we know the bond, we can now predict the force. We can then compare the forces between the two molecules. So if we start at the bottom, okay, carbon to hydrogen, all of those are non-polar covalent. Not particularly useful, but out here we have polar covalent because we have an electronegative oxygen causing that dipole, or sorry, causing that to be a polar covalent bond, which means we have a dipole-dipole force. Because I have a dipole-dipole force, I should now consider, do I have the secondary rules? The secondary rules being, do I have a hydrogen bonded to an oxygen? Yes, which means I have hydrogen bonding as the strongest force in that molecule, not dipole-dipole. Hydrogen bonding is one of the strongest forces we have access to, so it could very well be A. Of course, I circled B, so we take a look at B. When we go through and look at B, what do we see? You should see the sodium. Sodium is a metal. Metal-non-metal bonds are ionic bonds, which are super weak bonds, but they make very strong forces. So we end up with an electrostatic force versus hydrogen bonding. Electrostatic is a stronger force. That means it's going to require more energy to break that molecule away from molecules just like it. Its melting point goes higher. Okay? In 3, we again see that oxygen. We're looking at polar covalent bonds, which would suggest a dipole-dipole force. We would now, because I have a dipole-dipole, say, hey, do I have hydrogen bonding? Do I have a hydrogen bound to that oxygen?
Yes.
This is trickier. No. And we have to be careful with how we deal with our structures. And I think this is a bit unfortunate, but this is something that we consistently do within this class sometimes. This is why we had you draw out a bunch of Lewis structures. This is the Lewis structure for that compound. Do we have an oxygen bound to a hydrogen?
No.
No. So no hydrogen bonding. So what we have then is a dipole-dipole force, and a dipole-dipole force only, not hydrogen bonding. So that's our answer for 3A. If we move to 2B, what do we have in 2B? We still have the oxygen to carbon bond, so that's the same, but I also have an oxygen to hydrogen. So I still have a polar covalent bond, okay, that does generate a dipole-dipole. But I now also have the secondary condition that I have a hydrogen bond. The hydrogen bond is stronger than the dipole-dipole. I'm now comparing hydrogen bonding in 3B to dipole-dipole in 3A. Hydrogen bonding is a stronger force. 3B has the higher melting point.
Number 2.
Okay, so let's move up to number 2. Okay. We move into number 2. 2A, we look at that structure. Hopefully what we go through and see is that we see no elements of any sizable electronegativity. We just have carbons and hydrogens, which means the bond structure that we've got is non-polar covalent. Non-polar covalent bonds can only lead to London dispersion forces, which happens to be our weakest force. Okay, so that should already be a tip-off that 2A is probably not our answer because we're looking at the weakest force. Okay, so let's look at 2B.
It's the same as 3A.
Which was the same as 3A. So I do have a polar covalent bond, which leads to a dipole-dipole force. I don't have a hydrogen bonded to an oxygen, so there's no hydrogen bonding. I'm comparing dipole-dipole to London dispersion, which is the stronger force. Dipole-dipole, 2B is the answer.
Dipole-dipole is stronger than London dispersion.
Dipole-dipole is stronger than London dispersion, yes.
Just like theoretical, if you were like 1B and 2B, would 2B still be stronger than 1B? Because
We'll get to that because that's a next layer of difficulty beyond this. Okay? So in these 3 answers that we've gone through and discussed, 2, 3, and 4, remember I said this was in inverse order of difficulty. you are expected to be able to interpret 2, 3, 4. Those are relatively straightforward. It's just what is the strongest force, compare the strongest force between those compounds. That's the answer. Right, that's it. Okay. Why does that become a little bit more difficult when we move up to 1?
There's so many of them.
It's the same hydrocarbon chain.
If we go ahead and clean all the rest of those out, we have nonpolar covalent bonds, which leads to London dispersion forces. We have nonpolar covalent bonds, which leads to London dispersion forces. Okay. Why is that now so much trickier?
Because they end in the same force.
It's the exact same force. The exact same force, how do I decide which is stronger?
Which one's
The
smaller?
bigger one,
Okay.
one with more mass. You need
Since we
more energy.
started with Star Wars, all Jedis have the Force. Does that mean they're all equivalent in strength and awesomeness?
Yes.
No, why not?
Because they're all idiots.
Right. Some have
Well, if
more
they're
energy.
all idiots, then they all have the exact same strength.
Some have practice, there is.
Some have better practice. They have more of the force associated. They have more midichlorians in their bloodstream, so they're now stronger, faster, cooler than the ones that have fewer. Okay? They all have the force, but they have varying amounts of force. If we go through and compare A to B, what else changes? So when you look at the box I drew for A versus the box I drew for B, are those boxes the same? No.
Just has more.
One has more. One has more of that weak force, which means
It has more practice.
it's going to require more energy to break that molecule away from other similar molecules than A. More energy means higher melting point or boiling point. That is why 1B is now higher. Why is that question more difficult? We're moving to a next layer of interpretation. Our first interpretation is just the strength of the force. Is it there, is it not? But now we have to say, if that rule is equal, I have to move to another rule set. That new rule set is the amount of the force present. Right? Could I move to even further rule sets? Yes. Right? I can change how those atoms are arranged with respect to each other, which will also change how they interact. Right? Just take my word for it that we could draw these out kind of like this. If I took a look at that compound versus 1, 2, 3, 4, versus that compound. They have the exact same number of points, which means they have the same number of carbons, they have the same number of hydrogens. Right? Both of these are just carbons and hydrogens, which means they both have London dispersion forces. Which one has the higher melting point? Why are you saying the one on the left? The one on the right has 5 points too. 1, 2, 3, 4, 5 right in the middle. They have the exact same number of atoms, the exact same force. How would we decide which one has the higher melting point? We could go to experiment. So this sucks for anybody at home watching the video because you can't see this. So let's go to experiment. We have our two molecules. What keeps those two pieces of paper together? What force? The friction between them, right? Where they contact each other is partly what's keeping them together. It's the exact same material. Now what's going to keep those two pieces together?
Not much.
Not much. Why not much?
They don't have as much area.
There's less surface area to now come in contact between those individual molecules, which means there's less individual points for the force to have an attraction. When I remove that surface area, I now decrease the amount of force per individual molecule. When I take a look at the two molecules drawn on the board, the one on the left has the higher melting point than the one on the right, because the one on the left has a larger ability to interact with other particles, whereas the one on the right can only interact on that surface. There's less interaction, right? Which means it's easier to break that molecule away from other molecules, right? So we can look at the strength, we can look at the amount, but then we also have to look at shape, right? And all of those have kind of an interplay, and we should start with the easiest one to evaluate, which is the strength. Right? Then we can look at the amount. Then we can look at the shape. But what happens if we go completely bat crazy? Yeah. And we go through and we take a look at, okay, and again, again, you're just going to have to accept it because I don't want to draw it all out. (4A) versus my drawn structure. Each of the points on that is a carbon. Okay? We have lines representing the bonds between those carbons. Okay? And we'll also have hydrogens associated with that. So this formula, if we drew out the formula, 1, 2, 6, C10, H, H8. Right? That's the formula, chemical formula for that compound. If we compared these two compounds, which would you predict to have the higher melting point?
B.
Why A? We have hydrogen bonding. We have a stronger force in 4A. In my drawing, there's no strong force. We'd be looking at London dispersion forces. Hydrogen bonding is a stronger force than London dispersion. We would not expect B to have a stronger force, okay, because of the strength of the force. But what else changes between these two? The amount of atoms that went into each. There's significantly more atoms in the B structure. So I may have a weak force in B, but I got a ton of that weak force. Okay? You happen to visit family and you've got a nephew. Well, let's say a 5-year-old nephew, and the 5-year-old nephew runs up, oh, that's cute, cool, hi kid. Okay? Let's spin it around. That 5-year-old nephew's come running at you with a knife. You might pause a little bit, but you can probably just be like, I'm going to punt you, kid. Don't even try it. Okay? You clearly have the stronger force than your 5-year-old nephew. Let's make it your evil stepbrother's 5-year-old nephew. So at least they're evil, right? Okay, so you can punt them easily. Okay? But your evil stepbrother didn't just have one kid. He had 30. Now you get 30 of those evil little kids with knives coming running at you. You might be able to punt one of them, but probably the rest are going to knife you. Okay? It's not just the strength, it's also the amount. Okay? And when we look at individual comparisons, we're trying to limit that and make it as even a comparison as possible. Can we make things all sorts of messed up and make it all sorts of hell for you to be able to predict? Yes. Should we or would we?
Yeah.
No. Okay? In a real-world situation, we might ask you to start to think towards that level, but in a class period, we're concerned about the overall topics. So we could make it more difficult. We don't do that. That's why when we go through and look at these, 2, 3, 4 are all things you were expected to be able to come up with, because all we're really comparing is the strength of the force. If you go through and check, the amount of atoms in each case, or the mass, is roughly the same. One becomes more difficult because we're now shifting to a new paradigm. We have to look at the size. Right? But at the same time that we now shift to look at the size, what did I do to the force? I kept it constant. Right? We need to be able to come up with fair comparisons to allow us to evaluate and move through these things. Kind of make sense? Okay. Which kind of gets us to the next point. Process. So,
Oh boy.
In the other class, they're having a lot of problems with conversions. You guys are admittedly doing a little bit better with the conversions, so that's good, right? But the other class needed some help. Well, I figured why not? If you want help with conversions, here it is. Here's help. Right? We've gone through, and what we've been talking about through the class is processes. Everybody, oh, I'll never use chemistry again, so I don't need to study for it. I don't need to prepare for it. There may be 2 people in this classroom that is ever going to need chemistry again. Okay? Coming into a class is not about saying, I need art history in the future. That's not the point of education. The point of education is using the processes to evaluate an unknown subject. That's what you're trying to get out of this. How do I take some rules and think logically about the material to solve a problem? Right? Some of you need the chemistry content, so you have to work extra hard to make sure that not only do you learn the process about how to think, but you also learn the content. Right? The biggest point in this class is, what is the process? How do you go through and solve a question? This happens to be a process that works for conversions. Right? Step 1, write down the measurement unit and substance in your desired answer. God, we never talked about that. Yeah, we did. That was step 1. Every time we did a conversion, that is exactly what we did. Okay? You ask for steps. I gave you steps. Now I'm explicitly writing those steps down. Okay? Step 2, write down the given number, measurement substance to the extreme left. Oh yeah, no, dang it, we did that too. Step 3, come up with a conversion factor. Oh crap, we did that too. Yeah, all of these steps have already been outlined. Okay? What we're trying to do with these conversions is come up with a process that works every time. The part that becomes challenging is that you then need to recognize where some of those conversion factors come from. Because it's a chemistry class, those conversion factors are coming from the periodic table. They're coming from a chemical formula. They're coming from a chemical equation. You have to be able to do the chemistry content to recognize that, to go through and do the solves. But this is the solve that works all the way through. Okay? Use this to do all of your conversions. Shockingly, it works. This is why we've told you to do this. Okay? Because it works. Okay? One of the big things that I keep seeing students do is they'll move to that step 3, okay, which I know because of the copy paste didn't show it out as numbered steps. Well, this was 1, 2, 3. So they'll get to step 3 and immediately start writing a number. Ooh, I need to use the molar mass. So I'm going to put 132.905. What the hell is 132.905? Why are you using that? Okay? If you don't know why you're writing the number, then you shouldn't be writing the number. That's why in step 3, at the bottom of that step 3, what does it say? Do not use numbers. You should be writing the units, because the units will dictate what numbers you need to be using. So if you immediately start jumping to the numbers, you're going to put the wrong number in, and then you're going to force the units to match the number. Okay? Unfortunately, you can't do that correctly. Okay? Because you say, no, I want to use this number, so I'm just going to make the unit whatever I want. It doesn't work that way. You come up with the unit. That sets you an expression. You can then say, is that expression valid? If that is a valid expression, that means there's a numerical relationship. Find that numerical relationship, put the numbers in. Now you reset. You go back to step 1 because you have a new question and say, are those units the same? If they're not the same, you do it again, and you do it again, and you do it again. Okay? Most of the questions on the final will be single step, just like the multiple choice. Most of them are single conversions. Okay? They're testing at, did you get the basic pattern down? If you got the basic pattern, you're set, you're golden, you move through. Okay? If you don't have that basic pattern nailed down, you're just trying to multiply or divide by whatever random number you come up with. And that random number may very well have been correct when you practiced it on the exam or did practice outside of class. Because you saw the answer and you're like, oh, of course I divide by that number. You didn't divide by that number. You used the units to establish where your numbers went. Okay? Do not look at answers. Right? The answers don't solve. Okay? For those of you looking for this slide, it isn't in the slideshow because I just put it together. I just saw you start to flip. Okay? So if you want this information, you can take a picture of it now. I saw at least one person do that. The other option is I can post it on Canvas. I'm fine with that. You want me to post it on Canvas? Sure. Okay. I'll put it up on Canvas. I'll try and get it into an announcement to go through and deal with it. Remember, this just looks at conversions. There's lots of other stuff out there that doesn't do conversions. Right? There's some like molar mass. How do you figure out the molar mass for water? That's not a conversion. That's knowing that the periodic table has molar masses. You have to have that content. Kind of, sort of? Okay. So this sets us up for kind of this next part. Final exam prep. Okay? I would be lying if I said I felt I should just lecture through the rest of the semester with the rest of the content, because I don't feel I should do that because that content is relatively minimal. Okay? The biggest part of the content is the old stuff that I think we're really weak on. Some of you need to move into 151. I don't think you're ready for that. You need the practice backwards. Okay? So to prepare for that, we have the final exam to prepare for. Complete the practice exam. Okay? You get lots of people, oh, I did the practice exam. When did you do it? Oh, I did it on Tuesday. Well, the exam was Wednesday. You didn't study. You just did a bunch of random questions and hoped for the best. That's not studying. Studying means that's done this Friday. Ideally, it's already done. Okay? So let's look at that practice exam and think about it. What I want you to go through and do is do every question you think you know. It doesn't mean looking at it like, yeah, I think I kind of know. No, you don't. The instant you question, you skip it. You don't know. Move on. Do every question you're like, I know this answer. Every one of those questions, that's what I want you to do first. Once you've got those ones, you will check with me, okay? Or you'll check with the tutors. Okay? I only knew 5 questions, Mike. That's fine. Okay, you knew 5 questions. Let's look at those 5 questions. You got every single one of those 5 questions wrong. I don't want you studying anything other than those 5 questions, because you're going to go into the final thinking that you know that content. You don't. Okay? So what you need to do is figure out what you do know. Right? And this applies for all exams. Every exam you take. What do you know? Let's prove that you know it. That's what I want you to check. So Friday, I should be saying, because I got a couple different classes, 50, 60 emails of here are everything that I know what is right. Okay? And I will go through those quickly and just say no, 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 no. Or I'll just say, hey, that looks like an awesome job. Okay? Because there's nothing for me to complain about. Okay? After that, you'll go back. Anything you got wrong, you need to find 5 questions to practice it. Okay? Arguably, you should be finding 10, because these are questions that you think you know how to do, and you don't. You need to find where that error is. Okay? So you should be finding 5 questions to practice. Okay? After that, rank the blank questions according to difficulty. If you look at it and you're like, holy crap, I have no idea how to do that, don't study that question. You're already going to get it wrong. Don't do it. Okay? Look at the questions, you're like, I kind of think I could do that one. Okay? Don't do it. Find 5 questions just like it and do those 5. Once you've done those 5, then you can go back and complete that question. Then you can check with me to see if you got it right. If you got it right, cool. You've learned. You're moving forward. If you got it wrong, guess what? You find another 5 just like it. Okay? This is studying. Opening the book and reading is not studying. That's not going to help you. You need to be doing questions. Okay? Makes sense for a map? Okay? That's only 2 weeks. Literally 2 weeks, actually. Because the exam isn't next Wednesday, it's the following Wednesday. Okay? If you want to know where you need, how much time you need to spend, remember, I've got totals. I can tell you, send me an email. I've sent lots of people emails already about where they are, what they need to do to go through and get the grades that they can get. Okay? This is going to help you get there. Okay? That said, almost said, what you should be doing as well is be thinking about the process that you went through to solve. When you're finding those 5 other questions, it's not about trying to figure out what the answer is. It's trying to figure out the process behind it. Okay? How did you go through to get that answer? Because you're never going to see that question again. what you're going to see is a different question. You have to be able to recognize how to solve that new question. So it's the process that becomes important out of that. Okay? Is that depressing enough?
Nope.
Nope? Good.
We need some antidepressants.
Okay? So, this kind of puts us in a bind because what I've currently got set up right now is the rest of the content for the rest of the semester. We got half an hour. I bet I could burn that content in half an hour and literally just kind of run through it really fast so we can say, yep, it was covered. And if you encounter a question that was about that, you could be like, ooh, okay, that's what Mike covered in the last 5 minutes. Let's worry about it. Or, yeah, burning content is fun. Okay. Or what you can do is you've got 3 exams. In theory, you have 4 exams, so you have the practice exam. How many of you have that material? See, that makes me think, well, then maybe we should just burn content and not worry about those exams. Okay, because not everybody can be focused on that same material. So what I would say is our plan is for Monday and Wednesday, you come in with your old exams. You come in with the practice exam, and we start working questions. Okay, and it can be as simple as you just saying, hey, I want this solved. Show me how to solve it. Okay, I'm cool with that. Does that sound reasonable? So we'll burn kind of factual content today, and then we'll go back and just be like, solve stuff next week. And then what you guys will do the following week is you'll all like ace the final.
Do we have class on the Monday?
We do not have class the Monday of finals. Right? Friday, this Friday and next Friday, I will be holding extended office hours, okay? Which means probably about 9 in the morning to about 5 o'clock in the afternoon or evening, whichever you want to say, I will be holding office hours. I don't know where yet. Consider how many people will potentially be there. My office isn't going to fit it. Okay. So her office wouldn't fit it either. Okay. So at least temporarily, I'll be in the tutoring center. I think there's a room next door that I can get. Right, so if you have questions, you can come by and ask. That's all day. That's right through the middle of lunch. I don't want to sacrifice, eating lunch. Okay, I'll buy lunch. I'll buy a bunch of pizzas. Right? So come in hungry around lunch. You can eat pizza and get some answers. Okay? So let's burn our content. Heat versus temperature. Okay. What happens is I add heat to a piece of ice.
The temperature goes up.
The temperature goes up. Doesn't necessarily melt.
No.
If the temperature I'm starting at is negative 40 degrees Celsius, I can add heat. All that's going to happen is that ice is going to get warmer.
It's not gonna melt.
Okay. But it won't melt. So the temperature goes up. Okay, as I add that heat. Eventually what happens?
You get to a
It
point where
decides to start to melt, right? We've added enough intermolecular or force to break the intermolecular forces apart, and we now start to transition from that solid to the liquid. What happens to the temperature during that transition? It stays the same. This is why when you have an ice cube in water, it'll stay at 0 degrees Celsius until all of the ice is gone. So even though I'm adding heat, the temperature won't change because we're looking at a transition through the melting point. Eventually, what happens to the ice?
melts completely.
It melts completely. As I continue to add heat, what happens now? Right? The temperature of the water will now increase. And I can see it increase again until what? Until we hit 100 degrees Celsius. And at 100 degrees Celsius, what happens? It transitions. Again, no change in temperature until we're all gas. And so what we're looking at in this heat versus temperature is phase transitions and what's happening within it. We can constantly add heat but not see a temperature change. This becomes super relevant when we're looking at things like calorimetry. So if you were ever concerned about how to go through and determine how much energy was in food, Okay? It's looking at processes like this. This shows up a lot in 152. What we do in 150 or 130 is we look at this and we say, hey, look, it's a pretty curve. It goes up, it goes flat. It goes up, it goes flat. It goes up, and then it just continues to go up because we don't have another phase. Right? In 151, we go through and say, how much heat do you have to put in before it goes up again? Okay, so you actually have to start to quantify it. That involves things like specific heat, okay, which I don't want to talk about. Okay? So vapor pressure. If we take a look at vapor pressure, this is the same kind of concept as our melting point. If we take a look at a question here, based only on intermolecular attraction, predict which of the following liquids has the highest vapor pressure. Intermolecular attractions. Well, intermolecular attractions are another name for our forces. And we can know our forces based off of the bonds that they came from. So I can look at a structure and determine the bonds to then dictate what force comes out of it. So I look at A. I see a polar covalent bond. Come on, pen. Between O and H. That polar covalent bond leads to hydrogen bonding as a force. I can move to B. What do I see in B? Carbons to hydrogens and carbons to carbons. Those are all nonpolar covalent, which gets us London dispersion forces. I look at C. I have dipole-dipole. That oxygen gets me a polar covalent bond. I have a dipole-dipole. D. What's that last letter out there? Chlorine. Right? Halogen, that's one of our electronegative elements. We're looking at a halogen bound to a carbon. That's a polar covalent bond. How do we know that? It's not chlorine to chlorine. It's also not carbon to carbon. So it generates a dipole-dipole force. Next one. I've got that sulfur standing out in the middle. Is it sulfur to sulfur? No. Is it sulfur or is it carbon to hydrogen? No, which means we're getting a dipole-dipole force. So all I've done is gone through and ranked forces. Based off of that, what do you think the answer is? Or let's try it again. What do you think the answer is not? C, D, and E. They all have the same force. All of those are now eliminated. I know nothing about the rest of the question. I'm now down to a 50-50 shot. That's a pretty sweet move.
So what's the correlation between vapor pressure and attraction?
What is vapor pressure? The lower of the attraction between our individual particles, the higher the vapor pressure, because vapor pressure is a measure of the gas state. Right? So a higher vapor pressure means I have more gas. Well, the reason I have more gas is there's less attractive force between the particles.
So the answer would be B.
The answer is now B. Because London dispersion is a weaker force than hydrogen bonding. Right?
Yes.
We just reasoned our way through something that could be massively quantified. Yes. That's awesome. That is really cool. Just based off of knowing something about bonds and forces. That's really neat. Right? Where does that question come from? Because that format looks kind of familiar to me.
Multiple choice and balancing.
Multiple choice from the what?
Balancing.
Yeah, from the practice final. Right off the practice final. Yep. Copied and pasted. Okay. Solubility and miscibility. Okay, we've talked about solubility. Solubility rules, in fact, was something that popped up earlier in the semester. Solubility rules were dependent on what? Your solubility rules, you should immediately be thinking,
Like this, I was like,
no. A table, okay, a table or chart. When would you use that table or chart?
Predicting double replacement.
Predicting double replacement reactions. Right? So you see solubility rules, you should be thinking double replacement reactions. Right? Double replacement reactions are looking at ionic compounds. Notice we're looking at solubility coming in with bonds and forces, and if we look at the comparisons that we're making up there, right, why might we not be looking at those with our solubility rules?
There's no ionic.
The solubility rules were all about ionic compounds. Those aren't ionic compounds. We need a new rule set. Okay? So our rule set comes back to bonds and forces. Okay? Because at its simplest level, this is where these interactions are coming from. Okay? So solubility is the blanket statement for anything dissolving in something else. Literally anything. Miscibility is the ability of a liquid to dissolve in a liquid. Okay? By definition.
How would that work exactly? Because wouldn't a liquid of a denser state float on top of it?
So we could get liquids to separate based off of density. Solubility is a different aspect. If I take, say, Everclear, that's a bit rough, so I might dilute that. Let's try it this way, because I've been doing this lately. Cask strength whiskey. That might only apply to like 1 or 2 people. Okay, cask strength whiskey. You're like, ooh, you drink that, that's a bit rough. What do you do to cask strength with whiskey?
Mix it with something.
You usually mix something in. Okay?
Like a Coke.
If you're a traditionalist, what you should be doing is ice or a little bit of water. Okay? Whereas regular whiskey, God, you should not be putting Coke in cask strength whiskey. Just for the record. Okay? Regular whiskey, you shouldn't be putting ice or water in because a professional has gone through and said this is the proper concentration of alcohol to get the proper flavor out of it. Cask strength, they haven't diluted it. They haven't measured that out appropriately. They're allowing you the freedom to go through and do that. Cask strength's a better buy because you can dilute it
So you mix
as opposed to the other one.
vodka.
Okay? Vodka is an entirely different beast because that just is crap. So,
That would just kill you.
ethanol, back to our system here, ethanol or alcohol mixes with water. This is why when you go into the store, you can get whiskey, which has ethanol, alcohol in it. Okay? You could also buy Everclear. Okay? They both have alcohol in them. But if you take a shot of Everclear versus a shot of whiskey versus even, heck, a shot of beer, there's a pretty big differential there. What is that differential? The percent alcohol, because what's the rest of it? Water. Did water and alcohol evenly mix?
No.
If they didn't evenly mix, when you took that shot of beer, what would you see? Water and your pure alcohol. Do you see that? No. That's because water and alcohol evenly mix. Why do they evenly mix? They don't have the same density. They are miscible. Their intermolecular forces, according to our rule of thumb, like forces dissolve like forces. The statement that usually gets made is like dissolves like. Like what dissolves like what?
What was this?
Somebody's having a fight with the door, apparently. Okay? If we add the word forces, this helps us out. What are the forces in water? Water is a polar covalent bond, which means it has what force?
Dipole.
Dipole-dipole. Because I have a dipole-dipole force, what should I be looking for?
Partial charge.
Partial charge is by definition in the dipole-dipole force.
It's a hydrogen bond because it has oxygen.
I should be looking to see, is it a hydrogen bonding dipole-dipole? Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Yes. Which means the force I'm looking at there is not so much the dipole-dipole, but hydrogen bonding. I go through and take a look at ethanol. What do I find within ethanol? I find hydrogen bonding. So let's go back to our solubility rule, our rule of thumb, like forces dissolve like forces. Like hydrogen bonding, dissolve like hydrogen bonding.
Yes.
Hydrogen bonding is similar to hydrogen bonding. What happens? Those two mix. Right? How about the last one, or the next one? H2O and officially propane. Don't worry about knowing the name of that.
No. It doesn't have
H2O was H bonding, or hydrogen bonding.
It doesn't have a hydrogen bond.
That one's-
The other one
That one's London dispersion.
has London dispersion. Is hydrogen bonding similar to London dispersion? No. Are those forces similar? No. Do they mix?
Probably not.
No. Sure enough, what happens? They don't mix.
Even under pressure.
You can always make something happen. Don't make something happen unless the question tells you to make it happen. Okay? You have to be very careful on that statement. Every man in this woman can be made, man in this room can be made a woman. Okay? That doesn't mean that's how we should be starting our
So
statement.
when they make liquid propane, they're using heat pressure to take propane and put it in H2O.
They're not putting it in water.
They're just making
They are making gaseous propane a liquid, not aqueous, a liquid.
liquid propane.
Yep. That's a different process because you're not mixing two things. That's one thing.
Okay, so it's just a pressure.
That's just a pressure temperature thing. Yep. Okay. So what we're looking at for miscibility is just comparing the forces. The forces in each of the two compounds you're looking at mixing. Okay. So every time you're asked about a solubility question, you should be saying the forces in this compound are this, the forces in this other compound are this. Are those similar? If at any point you're asked a solubility question and you say the forces are this, you can't answer the question. Solubility is by definition the mixing of two things. You have to identify the forces in both those things.
So like if you just kind of wanted to physically see it, if you poured two different liquids and they separated, you could basically see the differences running through that?
Yes. So I could mix a liquid like gasoline with water, and I could see that they have a separation. What does that mean? The forces in gasoline are different than the forces in water. So that simple experiment now allows me to know something about the bonds and forces in each of those individual compounds.
So that, what's to say that different alcoholic drinks where you see different layers on them?
We have to be a little bit careful with the different layers in alcoholic drinks because they can separate by density if you force them to do so.
So if you had a hydrogen bonding liquid and you had a dipole-dipole liquid, would they somewhat mix because they're sort of
So
the
if
same?
we look at our wheel, the whole point is finding similarities and differences. So the first one, it was hydrogen bonding and hydrogen bonding. Well, they're both the same. The second one was hydrogen bonding and London dispersion. Well, they're both clearly different. Okay? The question now being asked is, what if I have a yellow hydrogen bonding force and a green hydrogen bonding force? Would I expect them to mix? Well, technically they're different colors. What is different? This is why it's a rule of thumb. Okay? It's an approximation that allows us to take a first stab at it, and then we hope for the best in the later parts. Okay? This is why when you're asked questions, you aren't being asked questions on the gradations of the color. You're being asked on the gradations of the forces in their absolutes. Okay? So don't worry about that unless you move into OK. Okay? What about ionic compounds? Okay? Water is hydrogen bonding. Our ionic compounds will be ionic. Those are technically different forces, right? So we might say they're not soluble. So when I take salt and add it to water, it doesn't dissolve, right?
It breaks down.
It does. It does dissolve. Why does it dissolve? Ionic compounds have an extra added complication as kind of a middle finger to everybody trying to solve them. Unfortunately, we have to worry about extra rules when it comes to ionic compounds, because our ionic compounds are really going to come down to, are they looking at the strength of a force, or are we looking at the strength of a bond? And it's pretty much the oscillation between those two that are going to dictate, do they dissolve in water? Okay? In the case of sodium chloride, that interaction is relatively weak. Because it is relatively weak, that puts it close enough to hydrogen bonding, and we don't expect to see it. If we look at potassium carbonate, also relatively weak, we expect to see them dissolve. But if I looked at, say, random, just pulling this out of my head because there's no particular relevance to, say, this compound ever in, say, like the lab you guys just completed, copper carbonate, what is the strength of the interaction between copper and carbonate? Turns out it's really, really strong because the solubility of copper carbonate is insoluble. It would be specified as a solid. How would I know that by just looking at it?
It says S.
I wouldn't. How would I figure that out?
Solubility rules?
The solubility rules. So the instant I have ionic compounds, I need to be referencing solubility rules. If I don't have ionic compounds, I can be looking at the rules of thumb pretty straightforward. Okay? Yeah, we don't need to see that. Well, there we go. Like dissolves like rule to predict which of the following liquids is miscible with water. Miscible means
Dissolves in the water.
dissolves.
Liquid dissolved in liquid.
Okay? So when you go through to do your homework and solves, just circling the answer is wrong. But miscible is a word. I could write dissolves next to it. There's some work. Okay? What's the next stage of work I could do with this?
Crossing up the ones that are obviously wrong.
Okay? How do I know they're obviously wrong? The forces. So maybe what I should be doing is identifying the forces. The forces for what?
Pentane, cyclic.
Okay, pentane, okay, LDF, LDF, dipole, dipole, hydrogen bonding, and that last one is LDF. Yes, you should be able to go through and do those roughly that quickly.
So all the LDF ones.
So you could eliminate all the LDF ones, okay.
Too many answers. Then you can,
It would just be D,
D, why D?
because it has hydrogen bonding the same as water.
Finish your statement. It has hydrogen bonding,
The same as water.
the same as water. We're missing a big piece of information here.
water.
It doesn't say what you're trying to.
Okay. It doesn't say what you're trying to dissolve. Apply like dissolves like rule to predict which of the following liquids is miscible with
Water.
water. Snap! It is there. Okay? That's unfortunate. English messed with us, and we didn't actually see the formulas. Okay? Are you expected to know the formula for water?
Yeah.
Yeah, sorry.
H2O.
You're supposed to know that it's H2O. You're supposed to know that H2O as a compound is going to give us what intermolecular force? Hydrogen bonding. Now that I have two forces, because remember where we started, solubility is two things. If you work through a question and you've only identified one, you can't solve the question. You need the second. Okay? Which you were right. You identified it, but you didn't write it down. Write it down. Okay? Maybe a handful of you are taking the full time on the exam. The rest of you are not. Okay? If you aren't writing this down, you're getting the answer wrong. Don't believe me? Look at your exam score. Sorry. Okay? Write that information down. We now have appropriate work. We could go through and even add an extra layer on this. Hydrogen bonding,
Miscible.
most similar. My answer is now D, glycerin. Okay? That is show your work. That's what you should be doing. Absolutely need to be doing it in the homework. You should absolutely be doing it on the exams too. Nitroglycerin explodes. Glycerin doesn't do anything.
What's it like?
What's that?
What's nitroglycerin?
Glycerin is the backbone of all of your fat. That's why we call them triglycerides. It's from glycerin.
We use glycerin paper to wrap TNT and it sits and sweats.
So, our next big aspect on content, acids and bases. Okay? We could go through and name these, and in the process of naming them, hopefully what we would know is that only one of these gets named an acid. Why does one of them get named an acid? It's AQ, and we have an H in front. That is our horrible crap definition for an acid, but that's the one we're working with. That is perfectly acceptable for the sake of this class. Right? The biggest part of that, okay, or the point that we need to be drawing attention to, is that it gets a different name because of its reactivity. Okay? Initial scientists were really just people making observations, and observationalists noted that some chemicals, when they made somebody stick their hand in it, melted that person's hand. Like, we should probably put a label on that, so I stopped putting other people's hands in it. Okay? Nice. You shouldn't have done it in the first place, but yeah, nice. Let's at least put the label on it. And so the label they came up with was acids. Okay? They also noticed that it also happened with this other weird solution. Melted someone's hands off. Okay? But it wasn't the same as the acid because when I mixed them, because I was like, oh, they both did the same thing, and I mixed them, it exploded. Whoa, okay. They both melt hands off, but they're not the same. So I'm going to call one an acid, I'm going to call one a base. This way I can tell people, don't stick your hand in those, because that's bad.
And don't mix them.
Okay? And don't mix them, because they're not the same thing.
But let's taste them.
Okay? The next part then comes from observationalists. This is why chemists usually live 15 years less than the average population, because of stupid things like this. We didn't have any other way to identify, so how do we identify an acid? Well, melting a hand off. We also happened to notice that the poor sap that we fed it to was like, this tastes sour. Right? And we knew it tasted sour. Oh, as it's melting my hand off, that's weird, it's sticking. Yep, that's cool, dude. Okay? You now don't have another hand, but thank you for the observation. So we noted that those substances that we called acids had these traits. They were sour tasting, okay? And they were sticky feeling. The bases were bitter tasting, okay? And slippery feeling. Kind of like, anybody growing up had parents that were like, oh, you said that four-letter word, eat this. Let's clean your mouth out with soap. Soap happens to be bitter tasting and slippery feeling. Guess what soap is? A base. And yet you smear your hands all over that skin melting thing? Right? Yes, we do. Not all acids and not all bases are going to melt your hand off. Right? We have to know something about their reactivity beyond that. Okay? Sour tasting and sticky feeling. Okay? Anybody eaten a lemon? Or made your baby eat a lemon? Hey, try this. Oh, yeah, it's fun. Okay? So, sour tasting. Okay? All citruses have acids in it. What's that acid?
Citric acid.
Citric acid, because it's a citrus. That's where the name came from. Okay? Those are acids. Those acids just don't happen to be strong enough to melt our face off. Okay? But they're strong enough to taste sour and be a little sticky feeling.
And tear your cheeks.
Right? So we could go through and look at acids and bases, and if I mix an acid and a base with each other, we end up producing water and a salt compound. Water comes in as a phase of a liquid. Each of the other compounds were aqueous. Change in phase means chemical reaction. Most chemical reactions are also correlated with the change in energy. It turns out all acid-base reactions produce energy. Okay? This is the whole why we don't mix them at large contents, because if we mix them at large contents, it tends to generate enough energy to cause water to boil. And if our container was small enough, it's now boiling acid and base all over you, and that's not particularly a good thing to do. Okay? So, the definitions that come out with our acids and bases. Okay? As soon as we started to learn more and get beyond just the observations, Arrhenius was the first one, or at least the first one given credit for defining what an acid is. He noted that it increases the concentration of hydrogen ions. So when we take HCl and I add it to water to make it aqueous, it produces H+. So that's how we decided to define acids. Okay? He also noted that there were species that were these bases that when he added them to water, they produced hydroxide. Right? Hydroxide is a complex ion. It's also one I told you to memorize. Why?
It's cold.
It's what makes it a base. Right? This definition, right, I'm a bit harsh on, for those of you that printed the slides, a bit harsh on calling completely and utterly useless, right? Because they're way too narrow a definition. They don't allow us to extrapolate out to all chemistry. So other scientists came through and refined those definitions to give us other ones. You get Bronsted-Lowry, you get Lewis. Right? Those definitions are broader. Okay? Lewis is so broad that we actually went, whoops, too far and backed off and came up with other definitions. Okay? The Bronsted-Lowry focused in just on the hydrogen. The acid was a proton donor, so we kept that from the Arrhenius. But what did the base do? What happened to the structure that looks most like NaOH? Became H2O. What did it do? It accepts a hydrogen. So acids lose a hydrogen, bases accept a hydrogen. Okay? With that definition, he could now go through and label this guy as a base. That one didn't have hydroxide in it. But now I have a better way of labeling that as a base because in the course of that reaction, it accepts a hydrogen. Right? So it's a slightly broader definition. It works a little bit better, and it tends to be one of the more accepted definitions for acids and bases. The next part is recognizing what happens as we go through and do a reaction. We encounter this concept of conjugate partners. So we take a look at that top reaction. In fact, yeah, let's do the top reaction. What would I expect that first compound in that top reaction to react as? Should it be an acid? Why should it not be an acid? It doesn't start with hydrogen. Perfect. That's all we wanted. Right? So that means it's going to act as a base. To act as a base, what does it need to do? It needs to accept a hydrogen. So if I wrote it on the other side, it'd be SO3, but it needs an H. So now it would be hydrogen sulfite with a -1 charge. Because I've only added one hydrogen. Hydrogen is just an H+. That's a -2. Okay? What happened to the H3O? It lost a hydrogen to become H2O. Okay? By using that information, I can now predict what happened. To head that direction, it acted as a base. To head that direction, it acted as an acid. Yeah? What is different about this reaction than any other reaction we've seen so far this semester?
It's a base and an acid together.
Nope, we've seen acids and bases before.
We didn't care about charges.
Charges is an important one, yeah.
Oh, wow.
That arrow in between goes both directions, which means I could just as easily be keeping my focus on the water, and I could take the water and go back. Whoops. For the water to reverse the reaction to go back over to here, what does the water have to do? It has to gain a hydrogen, which means what did that... Thank you. Which means it acted as a base. What happened to the other one? It lost a hydrogen, so it acted as?
An acid. Wow.
An acid.
That's terrifying.
Okay, which is super awesome, because if I ask which one's the acid,
Neither.
Both. Either. When?
I'd have to know a when, an aspect to define that. Okay? This is where I differ from the textbook and where I differ from the final. I define acids and bases as the reactants, okay, which we will call as our left-hand side of the equation. On the right-hand side, I still have an acid and a base, but those are product acid-base. So how can I differentiate and still keep the meaning that H2O needs to act as a base? It's a conjugate base. All right. By adding that extra term, I can now differentiate what species I'm looking at because it allows me to say the conjugates are the products, the other ones are the reactants. I don't lose the meaning of what that species is doing because water is still going to be a base, but it's going to be the conjugate base. It's the conjugate of what? H3O plus, because that's what it's oscillating back and forth between. It's merely a labeling system allowing us to define those species a little bit better. Didn't quite burn all of the content. There's a bunch of answers on there. Okay. What we'd be moving into is equilibrium. I'll talk really quickly, hopefully no more than 5 minutes, on this slide about equilibrium. On whatever it is, Monday. And then classes when we would meet next. That's when I'll talk about this. Right? This is just another fact thing, rates and equilibrium, what affects rates. So we'll present that. And then the rest of it is pretty much the end because we would just say what are our electrolytes. Okay? And you did